All right. So thanks everybody for coming. Last time it didn't work out so well, but we're ready to go now. And I'm going to slide over those things, see the screen better since my projector's not working as expected. We're going to talk about level programming, and I'm calling it a subspace of Scala, and we'll talk about what I mean by that shortly. And but this is from a product of some blogging I had done recently. I just know there's this big gap between like the Java guys that came into Scala and like the more academic, I guess, Haskell background and functional programming background guys that are in Scala. And they seem to just do all the typing stuff, and by typing I mean, of course, static typing, not typing on the keyboard. And but they're like way in another world that I didn't understand, and I'm like, okay, I get typing a little bit, but I don't understand anything they're up to. So this is just me exploring it, not coming here as an expert. It's just me saying, hey, here's some stuff I figured out, and it was pretty neat. And so I'm just going to share it with everybody. A little background on myself here, if I can get that. All right. I think it's always good to know a little bit about the speakers, not me just talking about myself. But I do have CSM math degrees, so that does influence the way I look at software a lot. And I did primarily Java from 2004 to 2013. And I started playing with Scala late in 2012, and now I write Scala all the time at Mental Graphics. And so I have a lot of experience with Scala now, but all of my thinking of software mostly comes more from a Java background and the way they approach software development. So it is planted that way. And so some of you may be worried, right? Oh, no, subspace, that sounds like math, right? It sounds like a vector subspace. Actually, has nothing to do with that. When I was working through this, I kind of realized, like, hey, this typing kind of has a weird parallel to value programming, and it made me think of this. Anybody remember playing this video game, Mario 2? You guys, or anybody not remember playing it? Like, just didn't roll that way? Yeah. So we'll talk about how I came up with this analogy a little bit. So the thing is, you know, this Mario 2, I think it came out in, what, 88 or something. It's been a while, right? No doubt. And but you know, it looks like this. Here's a little screenshot of the game. And this is, I'm comparing this to normal programming, normal value programming, which is, you know, here's Mario. There's good stuff. He can jump and climb, and he can get the little cherry over there for some good stuff. And there's these guys out to kill him. There's bad things, and, you know, you can pick up stuff. There's all these maneuvers and stuff. And you can do good things and accomplish things and get through the level and be on your way, and you do great. But it turns out there's this one cool little thing you can get here, and I'm calling it a flask of type programming. And I don't know if you happen to remember the little flask, but when you pick this thing up, you throw it down, you end up with a door. And you can, you might remember what's on the other side of the door. Like you go there and the whole world flips over, and you're in this weird black and white world. Well, that's what I'm comparing to type programming. You walk in, you flip over, and here you are, subspace. That's what the video game calls it, subspace. That's where I get the name. And but you can still do a lot of the same stuff, right? You can kind of run and jump. You're restricted. You can't move beyond the frame. I don't know if you remember that. You can't advance or back up on the frame. But there's some really cool stuff that you can get here that you cannot get in Value World, or as they call it, subcon in the video game. Like the mushroom there, and if you pick up the weeds here, they're coins that you can cash in for later for extra lives. And if you get the mushroom, you end up with the little dots that are over here. You end up with another dot, so you can survive a little longer. And so I kind of thought, like, man, that kind of reminds me of this game when I was getting a type program, because you can it's still got the same shape. It's kind of isomorphic, if you're okay with that word. And but there's stuff you can do there that you can't do otherwise, but you don't have to use it, right? You can get by without typing. We know that. There's dynamically typed languages that don't take advantage of it at all. And so that's what this is about. So throughout this, I'll kind of use these colors and things to kind of explain the way through as we go through Value Land. So let's look at a little bit of Scala code. So here's one way you can declare something, a val. It's going to be 6, right, when it evaluates. And the way a val is set up, it's immutable, that you can change it. But the important point I'm making here is when does this get evaluated? And it gets evaluated when the program hits this line. It'll say, oh, num, let me figure out what num is. It's 6. I'll put it in memory. Now, realistically, we know the compiler probably composites out to make it 6 immediately. The memory is assigned at the time of the line to see it. Now, if you've done some Haskell, you're more used to the lazy val, which is it'll see like, oh, I have a string, but I don't need it right now. I'll go evaluate it later. I'll just remember that I need a string, and until someone asks for it, I'm not actually going to compute ABC and make it a string. So it delays the calculation and the assignment to a later time. And then you can also do a def, which is a function, more like a function. And the same idea as lazy val, in that it doesn't evaluate when you first hit it, but it reevaluates every time you call it. So one common application, you might make a def called now. So every time you write now in your code, it will call this function, produce a new date, and get basically a timestamp. And so, again, these are three different declarations of the same stuff, but they happen at different times. And so it turns out that typing is really about the same. You get to type world, you get my map in this case, which is a map of int to string. It just gets evaluated a lot sooner. It gets evaluated at compile time rather than at runtime when it's invoked, or later when it's used and so forth. It's actually done immediately during compile time. And that's the main thing I started noticing about type programming. It's like, well, it's just computations that happen at compile time. And so we'll take a quick example here, and I'll try to take the time. Slow me down if I'm moving too fast, because I think only Dave here has experience with Scala outside of the rest of the group. And we're going to define some simple values. So again, we're back in value land, right? You can see Mario 2 back over here. And so we're going to define Booleans, real simple. That's the simplest it can get. And so the first thing you do is you can define a trait, which is basically an abstract class. You can't instantiate it directly. Still just means that within the scope of this file, I can extend it outside of kind of like a enum. It fills it up. Don't worry about case, but I can make an object. It's basically a singleton. Okay, that's not what I wanted to happen. How did I get that far out? That's really cool. I'm using Impress.js, which you noticed are wondering, and I'm always learning stuff that it can do and I didn't expect. So when I double click, it did something I didn't expect. Don't double click when you're using Impress.js. So I was trying to highlight objects, but it's not going to let me do that. Why is it going over here? So, but an object is, I'll say it's a singleton for the scope of this conversation. It's not really a singleton. Dave knows what I mean by that. But for here it is. So you got this true value, which is the Boolean or bool value, and you got the false, which are bool. Two different objects, right? And then you can define some operations. So we'll go back to the same code, but I'm going to add some functions here, right? I can have an abstract not for bool vals. I can have an or that takes the bool val, gives you the or logically. And once you implement these, it's pretty straightforward. If it's true, you have not as your false. And your or evaluates your true value. It doesn't matter if you get past true or false. If you do an or with true, it's always true. And similarly with false. The not is always true, and the or is always the other guy, that. Evaluates whatever he was. That's what becomes true. What's cool is you can define these as types, and it's really, really similar. It's just a little bit different syntax. So first thing you notice is at the very beginning it's the same, still trait, it's a bool type. But now instead of creating objects, I'm creating more traits, which are types, they're abstract types. And they both extend bool types of true and false. And you can do the same stuff. You can, I was going to first compare the two for you. There we go. And show you exact differences in the syntax. It's just a couple of different keywords. It's essentially the same. And that's what's kind of fun about this and it gets back to kind of like this optomorphic, right? You can do the same stuff, it's just at a different time. So now let's look at the trait. There's a little bit different syntax here. When I want to define a not, one, because it's a type by convention, you make it a capital N. Not really important usually, but sometimes Scala gets weird if you don't follow that convention when you do matches and that sort of thing. So it's good to follow that. And the other thing, instead of a colon, you get this less than colon thing that kind of just designates what type the type is, what's the super type. And also on your or, it takes a parameter instead of regular parentheses, right? You get the square brackets. And just to compare it to this guy, you can see. Yeah, it's basically extends. Yeah, it's saying this type is a subtype of this. It's assignable. It's really almost more of an assignable kind of thing. Just like you would with your values over here. It's like, well, this must be assigned a Boolean. Over there, it's saying, well, whatever this not is, it must be a bool type. And again, it's just some slight differences in syntax, but same kind of thing. We'll go on and look at true type. Again, it's pretty straightforward. It's just differences. Now we're saying it's types, and we're using capitals. And the logic is the same, right? False type is the not is true, and or is always true. And with that, and we can kind of look at these side by side, and you see they're basically the same. Just make a few little substitutions, and you got the type version of the value version.
It's still a trace.
But it's still a trace.
All types and true type are traces.
Right, right. And again, false type, the not is true, the or is always that, the thing that's passed in. And if you like to see that side by side, you can see it kind of here. And not a big deal, right? It's just pretty straightforward. But one of the questions that always comes up for me is, like, if I start writing code, how can I test it? And what's fun about this is you test your type stuff by compiling, right? You just need to have some test code, but all you have to do is compile it. You don't even have to run anything. And so we can actually look at some stuff that's in Scala that lets you do that. I don't know, Dave, if you have any more ideas on how this works. To me, it's just magic that works. Implicitly, if you want to check if two types are equivalent, you type implicitly. And I never really looked at why. I just kind of, okay, that's fine. I'll worry about why later. And but when you see that equal, colon, equal, if it's in, implicitly, it'll check if it's equal. And so this will not compile if these two types are not equal. Now, obviously it is because I'm just checking equality with itself. But that's like a little operator you can use to check equality. And you can also do, well, the question is, how about negative test cases? Because of course it compiles, but does the bad stuff not compile? That's really the big value in doing good typing, is can you make stuff not compile. Well, there's this library out there called Shapeless, and they've come up with some really cool stuff where you can actually say, this should be ill typed, and the string in there, if it doesn't compile, then the program compiles. But the opposite is also true. If that string has valid compiling Scala code in it, it would fail to compile. So they did some pretty cool stuff. It's using Scala's macros in order to pull that off. But you can kind of give a string to the compiler and decide how it compiles based on the result of that. And so you guys would test both directions. And just to show you some more examples and how you can start invoking these different objects is now you can go true type pound not. So to traverse down to a subtype or a member type, I should say, use pound instead of dot. Scala's like Java, it uses dot to call methods and members of your object or your class. Here, if you're in type world, sort of, you use the pound instead. And so all of these will compile and they look good. And similarly, if you have the or, which is text of parameters, you'll use square brackets. And so all of these will compile as expected, and that's how you can kind of test your code. And it's also nice examples of how it looks. But this is true and false, right? It's pretty easy. It's just two types. What's the big deal? It's really, you could maybe even do some of this in Java. I'm not sure. I didn't try. But what's really interesting is you can get nasty in the Scala type system. Because the Scala type system, if you give it the right compiler flag, well, you don't have to give it the compiler flag. If you don't, just do your warning. But it's Turing complete. So you can run a whole world of stuff inside the compiler, or it can never return. So that is kind of the bad thing, right? Your compiling is no longer deterministic. But that's okay, because you're just sitting there. You don't mind wasting your whole day finding out your program doesn't compile, right? So let's look at making an integer. You can actually define an integer recursively as a type. Again, to kind of introduce how you do that, I'll show you the values equivalent of how you do it. And this is the Pinot encoding, which is like 0, and then and so I shouldn't say int, I really should say natural numbers, but just whole numbers, whatever definition you like. Starting at 0, all the guys, 1 greater. And I'm also defining plus, just to make it fun, kind of add the two together. So I've got still trait, again, abstract class. Int val has a plus, takes another int. The 0 is an object, it's sort of singleton, the base case. And I've got my int in, which is sort of like the next int next. So I want a nice short name. That's the best I came up with. And it'll take whatever the previous value is, and he becomes the next one. And just to give you a taste of the recursion, then you can look at plus and see. To add another one, you just add him to your previous and wrap it back up as the next. And it took me a little bit of thinking to do that because even though I've got a math background, I did do a lot of recursion for a while and kind of had to get back to it. But that'll add it up, right? It's the previous one plus the next one plus 1. And it works. Does that make you feel good, or you got questions about it? I mean, you have to look at it. I don't know how comfortable everyone is with recursion. We can look at some examples here. This is some test code. This is legitimate Scala code too, by the way, if you're not used to seeing it. So your number 1 is going to be int n, apply to 0, then 2 and 3. And then this is using Scala test. So actually I messed up my, no I didn't. I got the list. Int 0 should equal int 0 and so forth. You also can do, this should not, yeah, the second one should not equal. And say my plus operator, that's kind of how it works. You can drop the dot in the parentheses in most cases with Scala. I don't even fully understand all the rules. I just do it to the compiler complain. Yeah, I could have, but I wanted to. The reason I didn't is because to make the type a plus, I think was the problem.
Oh, okay.
Yeah, so I went with the word plus. Yeah, I know. It's a cool way to do it is use plus sign, but I was like, it's okay. And but I was looking at the type version of it. So again, it's all the same stuff. You just change the syntax a little bit. And so now we got the int trait. Well, if I have the int 0 trait, we don't have to do anything to make it an object, right? A single thing is just a type, And what's cool though is your types can depend on other types. So my int n is a type which takes the previous type, and you also have the plus and all that stuff defined. And again, the logic's the same, it's just different syntax. Just like you flip the world over, change your syntax, and you got types instead of values. And but it's exactly the same. Up and side by side, apparently not. Again, go back. Sure. Yeah. Any other questions? I can mow through the presentation, so you always got to stop me. The timing should work out. There's plenty of time for questions, so don't hesitate. So series, I did the same thing as I did with the last one. I defined 1, 2, 3, and showed how you would test these and so forth. Implicitly that they're going to be either the same, or if they're not the same, use your ill types. And 1, 2, 3, you can do the addition over there. It works. It was pretty cool. I didn't really tell how to add things differently than I did my values. I'm just like, here you go. And it just kind of works out. But who cares, right? It's just, how neat, dude. You do a bunch of types and types and types. Now, I'm real pragmatic with my software development. As much as I love my math background and stuff, I really take the approach of like, how can I build something useful? Okay, now tell me how that worked. And that's kind of my general approach to things. So if you show me a bunch of type theory and go, yeah, I don't really know why I should care, right? I can come up with weird stuff. But like I took a lot of graph theory in school, and the reason I enjoyed that so much is at that time I was working at Atran, which is a lot of networking stuff. I'm like, oh yeah, I understand the application of graph. This is very important. Now I understand the theory. And so my whole approach, I hope you see so far, is very pragmatic. And so I did all these types. I'm like, well, this is cool, but who cares, right? Well, you can do some fun stuff with your numbers. So for the example I went with in my blog series post, or blog post series, is that I was like, okay, let me make a list of integers. And I'm going to make the length of the int list in the type system. Can I do that? And so this is where we start to bridge the world of like, okay, we got the mushroom, the cool stuff in the type world. Can we go back to the value world and be more awesome? And actually, yeah, maybe, So here's my int list. Again, try to make it real simple. I can have an int list, has some size, and by the way, this is how you would do it without, sorry to say this, this is the way you would do it without the type for your size, because it's just a value here. You got your nil. If you're used to Scala, nil is kind of like the empty set or the empty list rather, and its size is 0. And then I got my impl, right, which is head and tail, so I'm just kind of doing a show recursive, or I don't want to call it that, but head tail linked list kind of thing. And so my int list, is just size 1 plus the size of his tail, and it has a head element and then the rest of them kind of thing. So it's just recursively built up. Putting a new head element on each one. And what else we got? So a couple of other functions. I try not to put all this in at once and crowd it. So I say, okay, let's make some cool stuff. I don't know if you can read the comments real well on that background, but it says convenience list constructor. Then Dave will be like, oh yeah, double colon, that's cool. If you're used to Scala, you see that a lot. And but also defining plus sign. It's not I'm using the plus sign, but for vector addition. Remember from the good old days of linear algebra, vector addition, it has the constraint that the two lists must be the same size, or two vectors, right? You cannot add a size 2 vector to a size 3. It's no good. It's not defined. Can't do it. And so that's what we're defining here. Given two lists of the same size, add up all the elements. And again, I still have the size there just for context of the way it should look. And here's some usage. Instead of showing you the code, I thought, hey, let's show some usage of how this looks. So you can define a list like this. Just 1, double colon, 2, double colon, nil, and adding through 4, and that sum should be 4, 6, right? Because I got 2 lists, add them up, they're the same size, it's all good. And then this next one is, again, some Scala tests. So I should be able to add up 1 and 2 to 5, because they're not the same size. I should throw an exception. And if you're interested, here's what the code will look like. So for my int nil case, I should require, again, that's Scala syntax, you say requires, if the Boolean expression there fails, it throws a runtime exception. Don't require that to be me, right? I'm the only nil set on the object, right? There's no empty one, so you're required to be me if you want to add to this. Otherwise, it should just be this, no off. And my size is still 0. The more interesting one is, and this is where I do get worried about showing this much code in a presentation, but this one has a little bit. But again, the addition is requires the size to be equal. Otherwise, it'll throw an exception. And then we do a pattern match. So once we know our size is equal, we'll match and get the int. We'll grab the head, add those 2 values up, and then append it to the tails added up, and it's recursively, let it take care of itself. Again, this whole presentation is recursion heavy, so and that's kind of how you got to go with types. And then the size is the same as it was before. Right. Good with that? The recursion? So then you're like, well, we're validating size at runtime, but when do we actually know the size of those lists? When you say 1 double colon 2 double colon nil, it's at compile time. You already know the size of 2. You don't have to compute that at runtime. So that's where it gets kind of fun. Like you can say, hey, these lists are immutable too. That's another thing. This is not mutable lists like you get in Java where you have to worry about, I can't do compile time crap because it's going to change on me. And so we can actually take the same junk we just did, but now let's make it put our types, our size into the type system. And using the same int we defined a couple slides ago, you can say, okay, well, I've got a trait. It's my int list. It has a size. It's type int, int type. Got my object still, my int nil, because I'm still making value lists. I'm not making compile time lists. I'm just compile time checking the length of my value list. Okay with that? I know that was a lot of value in type words together. And then, so the declarations of the object, the case class is the same. It's just that now I'm actually putting those sizes into the type system by putting those type brackets there. And yes. Yes, it's the way you would say parameterized types. In Java, it's the angle brackets. They do square instead in Scala. It's exactly the same as that. And then, but then you also get that operator over there, that arrow colon that says, well, this type is really one of these types. And so you can kind of have dependent types that way. And now if we look at our int list with the double colon, constructor and the addition defined. Well, the double colon one is, again, we can just define it here and it's all good because it doesn't matter if it's the nil case or the other case. Is that you've given a head and for giving a head to ourselves, how you form the results of that? Well, it's just an int list simple with head and then myself. I'm now the tail piece in its head. And the type is my size up 1. So that's why I put down the signature on the second line int list of size 1 more than me, size n next, the next size up. And take the head, put it there, and return myself as the tail. One minor thing you may be kind of wondering about is when a function in Scala begins with a colon, is that right? If it begins with a colon, it's right associative.
I never figured out if it's begin and end.
Right. I can't ever remember, especially when it's double colon, you don't know.
You don't know.
But I think it points at the collection. So I guess if it's on the, it doesn't matter. What it means is it's flipped over, so it might be kind of odd that you're passing head as a function, as a call to yourself, and head is really on the front of it. But maybe no one's getting confused, and I just get more confusing about saying that. So what I'm talking about here, 1 is the head of the list, 2 nil. And so it is if you have the colon, I think on the right, it flips it over. Actually applies the method to the guy on the right to the left. So you can do evil stuff, confuse people. And so the same code as we had before. The cool thing is, like, screw the illegal argument exception. Scrap only compile. Like it won't work because now the type says you can't do that. When you add two together, we go back to slide. The sum with that must be an int list of size, which is bound up here at the top to my size. So it's saying I can only take another list with my size. Otherwise, it doesn't compile. So it's very declarative. That's another thing I found was a little bit of a challenge going into the typing because everything is just like here it is. It's not imperative at all. And so you just say it and it takes care of itself. So that right there, that it'll type is good. It'll compile the code, the string doesn't. And so looking in on some of the implementations here, when you look at the int nil, this one's easy because it's again it's just this. But the cool thing is look how much less code it is, and it's less code and it works better. Because I omitted size because I'm saying, well, my size is a type, so I don't have to actually have a value. But you could have that if you like. But like I didn't have to do all this stuff. I just said no, int 0. Like that's it. The compiler will take care of it for me. So I find the error sooner and I write less code. Then we can look at the impl of questions.
Yeah.
Right. Once you get your type system right, yeah. It's not that it's completely free, but it's just a lot less code. And but it's checked at a good time. So here, when you do the list impl, so this is like your general case, right? You need the size of your tail, right? Because you're just you're in a list with one more, right? You got your tail and you have the head. You probably could have made it such this was size, but I didn't mess with that. So then there, I've got my tail bound up to the side here on the second line. And then I extend the int list of the next, right, of size n of tail, right, because I'm one more, I have a head on top of that. And then the cool thing is this addition, once again, works out nicely, is that I say, well, that you passed to me must also be one greater than my tail size. And then I just do a pattern match. And for Java folks, it's almost like reflection. I'll say that very loosely. It might even be implemented using reflection. I'm not sure. It is. That's what I saw. So it basically is reflection. So it's like, oh, if this is an int list simple, which it must be because the sizes are matched, grab the head and tail, add up the head, and the tails added up like we saw earlier. But again, the big win here is just to check that compile time. And what else we got here? Oh yeah, so this was like, okay, that was cool. That's when they equaled each other. Can we do something more interesting? Kind of do a double plus. So again, Dave, double plus is, so he knows what it is already. But what's cool about this too, I probably shouldn't have you say this. I wondered if anybody could actually, maybe even guess what it is. So if you look at this operator, well, it takes that size, so the size of that guy is passed in. You see, oh, yes, there's that. And it returns a size plus that. And within the type system, you kind of look at that and say, well, this probably doesn't sum them up because I'm going to have too many elements. You know, you can actually start to reason about what this function is going to do without any comments. You know, just programmatically, the stuff that defines it is just telling, oh, well, that size, what's this one? I don't know if it's flipped this way or that way. It might be backwards. There are things I don't know. But there is one thing I know for sure, and the compiler knows is that, by God, this resulting list is going to be the size of both of them added together. And again, as Dave was mentioning, or not, we're talking about, I use plus here because the plus sign doesn't work out nicely at the time. And I went okay with all this junk to define this. So it's ugly. That's one thing I did learn about this type stuff, is that it doesn't look pretty. Scala tends to look nice and be happy and all that, but when you have to do all the type stuff, it gets you got a lot of weird symbols. So our int nil. Again, this one's really straightforward, right? Okay, you pass me that one, and I just return that because I'm nil. I've got nothing. So he concatenated with anything is the other guy. So his is really simple, straightforward. Then we look at this guy. Again, the class, case class definition is all the same. The difference is the double plus. So given that guy, give it to me. I love this recursion. It took me forever to figure this one out. Then when we got it, I'm like, oh, that's so small. It's another list with my head and my tail concatenated with that. Again, because I pulled the head off of it, it's recursive, and it eventually get down to the base case of the nil guy. So that one was a lot of fun to write. And the nice thing is the type matches up. One thing I keep forgetting, if you're not used to Scala, you know, I didn't actually put the return type here. It does type inference. And it actually infer that this little expression here is the type of the thing I'm overriding, because it looks at that and says, oh yeah, that's cool. So it'll make sure that those types are equal. We're okay with that? That's both sides. So then just showing you an example of how this stuff looks once it's thrown together is, so now I can take my 1, 2 list, and I can concatenate it with 3, and then take that guy and add it to 4, 5, 6, and it should equal 5, 7, 9. So you can just start making all these things. And it was just kind of crazy because, like, I don't have to do anything to make these things not compile when it's not good. It just works, as far as I could tell. Now, there was one thing, somebody commented on one of the blog posts. He said, well, when I'm inside the impl list where the size is abstract, he did something where the addition was not commutative. And that was really weird. I was very surprised to see that. Somehow it didn't, I think he had an implicitly thing that, well, if I add this to this one and then I swap them, it wouldn't come out as equal. So there is some room to explore here for me to kind of figure out, oh, why is that? That was very unexpected, because every other case seemed to work. So there's a lot more I could do with this. I just haven't really had time to mess with it much anymore. So, well, any questions or anything about this before I go on? Because I'm going through, and I personally made it like there would be plenty of time for us to discuss and things afterwards. So we're just knocking me an hour presentation.
This is the first talk I've heard.
Yeah.
Moving my mind right now. I mean, it's not even like way more complicated than normal Scala, so it's like.
Yeah, and that's why I was kind of worried about doing this presentation. Well, this is fun, but unfortunately, I don't know if anybody other than Dave has done a lot of Scala. But
I mean, you did a lot of sort of building things out from scratch.
Yeah.
In the Scala type system, the library Shapeless, it's got a lot of tools for sort of building different things and building them up.
Yeah.
Implicitly sort of use them. I think what the biggest thing that people take advantage of Shapeless, they call it H-list.
Yeah, the H-list.
Which is, it's a type, normally if you have a type list, you can say, okay, this is the type of my list. It's a list of, foods or widgets or whatever. And it tends to, the type of the list tends to take on the most generic type of the thing there. With an H-list, you can actually individually type individual items to the list, and it carries along with it as you build stuff.
Yeah, it's like a tuple meets the list.
Yeah.
Because it's a little more flexible than a tuple, I guess, because, well, now with Scala 2.11, there's no 22 bound anymore. You can go beyond 22. So does that make the H-list less useful?
I think there is. No, I think it's still there because there are things you still can work on it as a list. You can still read it
That's true.
as a list. But the type system will give you errors if you ever say, well, this is supposed to be a list with an int and a string and this type of object, and you get two strings and that type of object.
Yeah, and the H means heterogeneous, or genius. I would say that it's a list of different stuff. But yeah, the Shapeless is
I think
crazy.
what you find is that people, it's less about building these stuff for yourself from scratch. You find things like Shapeless where someone has done all the hard math.
Right.
They have some
That's right. Yeah.
At a bit of a higher level.
Yeah, and for me, it was just sort of like, well, what am I even dealing with? And I found out, well, really, I'm dealing with the same stuff as values. It's just at a different time with different syntax. For the most part, I can still do the same kind of stuff, but make really cool things that I can take with me.
I mean, you're doing Scala like you're in the day job at Mental.
Yeah.
So have you pulled off any of this and gotten into a overview where people did pull their hair out saying, what are you doing with this?
So the answer is no. I've not done anything like this at all. And what I've kind of learned from working with Scala is, like, if you want to do some really cool typing stuff, it's usually because you're writing a library for someone else to call, right? You're saying, like, let me just really make this API rock solid so you can't screw up. Well, when it's just us in the code building the application, I just don't see that as useful, because you're usually just like, well, it also would certainly depend on the libraries you're using. One thing, we're using Akka, which is like the anti-static typing, library of Scala, because it's like fundamentally not, forget it.
Yes, so for everyone, Akka is, so Scala has a lot of work they put into the language in order to support static typing and to support it in a way that's much better than what Java has. Not quite as flexible as elaborate as Haskell.
Right.
Akka is like their type a message to an actor, and he may or may not respond to this type of message. But if you have, there are like protocols and you read your messages and you say, okay, this is the message that I expect, and here's the response that I expect from the messages. But it's sort of vague into the type system of message itself. So it can't be like, I can send it to this object, and I get back a string message to this object, and it's keep click.
Right.
And that's sort of baked into the message itself, which, you know, it says a thing.
Yeah, it is what it is. It's kind of straight off.
Like the Okta is like one of the, and the thing that people use Okta for is building big scale systems, because the actor model works really, really well for that.
Yeah.
It also allows you to reason about threading, and it also allows you to reason about the district. Because with actors, when you send a message to the actor, it actually doesn't matter if that actor is on both systems or another. And it can, because the message has to pull that off, where it's like RPC, where it's a remote procedure call where you block waiting on the response, that will always fail every time. So.
Yeah, when I got into Okta, I just kind of related most everything back to EJBs. It's almost like having a stateful bean and a message-driven bean at the same time, because they can't have state inside them, but they can, but they just respond to messages that come in. They're sort of in a bubble, like you're saying, and that bubble can exist on a different JVM and a different machine or the same one. It doesn't matter. And it's actually really similar to the services we wrote back at Atran. It's very similar. It's like I made so many parallels to how that works, because you got a separation of, like, here's the actor, the actual object. You never get a reference to that. You only get a reference to a little cover, or so to speak, sort of proxy, and that's what allows that actor to be anywhere. Oh, yeah? Oh, interesting. Yeah, we'll have to talk about that. That'd be good. So it sounds like you're using it a little bit, or at least experimenting with it. Cool. But yeah, that's the thing with because we're using Okta a lot. We're using Lisp, and so Lisp kind of does our HTML stuff. And then when we get our request or whatever we want to do, we throw it in Okta and let it go all over the place and come back. There's some challenges with mixing the two, but yeah, it's not too bad. It's coming along really well. We're making something useful, and that's what matters, right? And so yeah, back to answer your question, I've not used this much, but what it would help me is, again, going back to Atran when I was working on the S&P Scala library for fun, is that, because, I mean, that was like, this is a great opportunity to try to really find out what Scala does as a DSL language, you know, kind of make it, like, slow, like S&P does as far as how it's typed. And so you could do a lot of type checking there that would be really cool. So if I was still messing around with that, that's where I would use it. But again, it's because it's a library and you're trying to help your library consumers do the right thing and compile check it. But within your own application, when you're calling libraries more so than anything, I've not found the need for it yet. But it's some good stuff. And then you have comments. I mean, I've still got a few more things we can talk about, but yeah, go ahead.
Yeah, it is understanding some stuff. I'm trying to think.
All right.
So, actual practical experience. So, I guess you would do something like show it. It's really like characters with the really tech against operations on money to leave.
Right.
So we have the ability to go in and define the type of thing. Hey, that's
right.
That's sort of,
yeah.
that's why you do.
Well, another
figure about that level of check.
Right. Another example I saw on like Stack Overflow, someone was asking, like, if I ask for a range, like, give me a range, beginning and end, but I always want it to be positive, or I always want, you know, the start to be greater or less than the end of the range.
Right.
You could potentially incorporate some typing to make sure that you always get past something valid.
Well, that's really that question. So that can be arbitrary. So length is still our, what it takes to our function of it. Right. But you could, the thing, you know, is 3 points to define a triangle, and only when the operations on the line area is triangle.
Right. But it has to be a real triangle.
Well, you define that as your type.
Yeah.
And then we check.
Right.
That tells you that it's 2 areas of the same, but whatever the function.
That's right. You could potentially do that.
Arbitrary.
Yeah, you're right. And I just picked lists and links because I And again, I think I did this over about 4 different blog posts, so I just kind of developed it as I went, and I made it more float a little bit more, in one piece when I made this presentation for it. But yeah, I was kind of like, hey, I got an int. What could I do with the entities? Oh, I know, the link to the list, and I took off with it there. So yeah, it's absolutely arbitrary.
That's the hardest one. Is that when you see that it's used a lot? Is basically allowing individual programmers to find this is what I care about, checking this, and now this provides me the way to find that type of
yeah. Right. Yeah, and if you make it allows you to write really good APIs for people to call that are more type safe than just the shape of the object, right? That you can put more bounds on anything because it's Turing complete in theory, right? You can come up with anything, and it might take the compiler half a day to run, depending on how complex you make it, and but you can always know that the caller of your API didn't do the wrong thing, assuming you wrote it correctly. Yeah, you're still writing code.
You could apply that much maybe for
right.
The compile.
Exactly. That's right.
You remind me of a talk a long time ago. There was a half thing, but it was basically so that the type of stuff detected the program added the incident but
that was Greg Bacon, wasn't it? He showed us that.
Dude.
Yeah.
Okay, yeah, this was
it's been a while.
Long time. Like it wouldn't compile.
Right, it wouldn't compile because it was infinite.
Greg had a similar thing. I can't remember if his was with where there was a missing case.
Yeah, it was something. It wasn't closed up somehow.
It was a Haskell thing, but some of those very things where the Haskell program wasn't compiled because type didn't enough.
Yeah.
And it was not obvious from what the function was written for. And then we figured out, oh yeah, of course. Yeah. And it's interesting in Haskell is you analyze code, changes your return type and nothing compiled.
Yeah. And so yeah, that's actually so I'll just kind of step through some of these. I made a retrospective because we're all up and doing Agile and everything now. And so I was kind of I'll do a retro for my slides, right? And so I already said this. So types are not just the shapes of objects. It's just values, but at different times, just like it is at runtime. And the other thing, and it's kind of get what you're talking about, it just expedites computation and compile time. It's like these things I was going to check anyway, like the length of my list, but instead of doing it at runtime, I would do it at compile time because I know it sooner. How soon do I know it? Let's do it then. And the other thing too is that guarantees I see the errors and not the users. That is kind of a good thing. If I can successfully put all this into my compiler, it might be like, oh, it's just a pain. I can't get this to compile, and you complain and you blame the compiler. But really, you're seeing all the errors instead of users, so that's always a good thing. And one other thing I kind of thought about is that these type validations kind of propagate through the code base. I don't know if that was evident from the presentation I gave, but when you're working with that concatenation double plus and the single plus, like all of that correctness that the API wrote for me, assuming I was consuming an API, it goes through all of my code. I can never mess up a concatenation and then a sum. I just can't do it. It's not going to be a valid program. It won't compile. And so that's the kind of nice thing, whereas, if you're used to protecting yourself with unit tests, it's like, well, anytime I do a sum, I have to make sure that I'm passing it good stuff. But, meaning that I'll have to make sure my code doesn't cause the runtime exception. And so that's another thing I thought was really cool about this is the way it kind of permeates through your code base. And so we're already sort of on this. If you're on my team, you hear me say this all the time. If there are questions, comments, or concerns, it's kind of how I end something. So we're already kind of talking about that. But it's just we're hitting all around the stuff that I kind of had on there and wanted to make sure I made those points. And it was just really neat stuff, especially when it just worked. It was one of those because it's new and you're like, this ain't gonna work. Oh, that does work. How does it do that? And it was a lot of fun. But yeah, any other? One thing I will say too about this, when I looked at this list, I'm like, well, it'd be interesting to have someone who knows Haskell really well, especially because I'm like, well, that's great if I type my list into my code, but what if I'm reading stuff in, you know, or obviously I can't know it at compile time.
So that's kind of like late evaluation. What's the story?
No, it still types out okay. It's just you know, maybe the length in this particular example would not pan out well because you need to know at compile time the length of that list for that type to be valid. But lazy evaluation, all that stuff still has a type, you know, associated with it.
It's just not all functions, so there are.
Right. Yeah, because, you know, at the end of the day, I know, speaking of Greg, he said this a lot during his Haskell presentation, is that, like, at the end of the day, we're going to do more than warm the CPU. So we're going to take input and do stuff and provide output. And so in those cases, it's fundamentally not a compile time. So those things, like, you can do a lot, and, you know, they have the monads and the IO monad and all that stuff where they really try to make it as safe as they can imagine being possible. But still, fundamentally, it's happening at runtime. So anything that happens, it could be known at compile time, you can encode it.
I'm in the Coursera course, so I
know
I don't know it, but I know this is the thing that works, we get all that. You know, everything that's visible. Then you throw a bar.
Yeah, you throw that in there. The link thing is no good.
You change, you just have to say no bar.
Yes, that has been my my policy to the team and my mind we adopted. I don't like enforce things that but coming in and like if we use Scala, this is what we got to do. And there are cases I think where you can use vars, but I've not had to do it yet. Especially with Akka, right? You do the become, and you can always change yourself. So you can kind of sneaky ways to still be quote unquote functional, but not have vars. But because
what you find is that mutability becomes sort of like this weird thing. You want to push off into a corner case, and you stay away from it. The hard part
right.
to do it becomes, you know, hide it behind layers of abstraction. Yeah, instead, like with Akka. Typically, your actor does have members that are vars because your actor is stateful. This makes it stay with response members. And those things we did, I did like recall this call.
I know. Yeah, it's heralded as like one of the greatest libraries.
Yeah. It's really fast.
It really is.
You can build scale have a very small.
Yeah. And you can test it really easily too. The testing framework template is really good because it takes advantage of that, you know, separation of the actor itself from the reference that you have, which is just like a little portal where you can throw messages at them of any type. And but yeah, we did. And what's funny is because especially, you know, me coming back from all these years of Java development, it took me a while to start thinking like, okay, I can't change anything. How in the world do I program? You know, it's ridiculous. And but now that I've gotten used to it, I'm like, how in the world did I have all this crap changing? It makes sense on my programs. So I got two junior guys on the team, and they're both really sharp, but it's new for them too. And we had there's a case class, and so case classes that you really want those to be immutable. I mean, I think if you put a var on those, I mean,
you have to try hard.
Yeah, like it would just not work well. Right, because the equals and all that crap would be questionable.
Well, yeah.
All that stuff. And so, but anyway, the moral of the story was one of the junior guys couldn't figure out how to do some certain things without, you know, variables. So he put variables inside the case class. I'm like, now this is fundamentally the worst place to put it because it's a message between actors, and now there's mutable state movement between them. So it's like all bets are off, and that's of course where the purists that are in the Haskell will say, well, Scala's no good because you can put a var in there, you can't guarantee, you know, blah, blah, blah. But, yeah, I'm okay with that. I just, you know, I'm good with coding standards. Especially with var, right? You can grep for that. Not a big deal. So it's kind of like a lint compiler. Linter for Scala. Anything else? Time is it? Did we do good on time? Wait. Not bad. All right. Yeah. Good to get up. I'm going to stop recording. I wonder how well I'm picking up all the questions. Well, I'm using a mic that should a little bit. I can't see if I'm not good enough that far away to hit stop.